Okay, so let's talk about wave motion with sine and cosine graphs. So for that one, I'll just start defining the things. And the actual use of sine and cosine waves in actual physics and things like that get a little bit more into calculus things, which is not difficult, but it just requires some prerequisites of calculus. So I will sort of just try to motivate it, but won't go into all the explanation of everything, since that would just require the whole understanding of calculus, which again is not hard, but it's just we don't have enough time to do that in this short video. So we already drew the sine and cosine graphs, and then they looked already very wave-like. But the whole point is, actual waves are normally waves in time, right? So as time passes, something goes up and down, up and down, up and down. So if we graph something over time, it looks like this. So how do we actually, specify how much time it takes for, a certain wave to repeat, or for a certain, how do we specify, how big the wave is and things like that, in a graph format? Well, it's actually quite simple. One thing is, this is going to be the unit circle again. And now, we actually want to generate a wave. So let's just pretend like there's a wall, right? And now you have a ball, or maybe a bead. So this is like a loop, it's a loop of wire, and then you attach a bead on it, so it's like a bracelet with one bead, right? And then you have a light here, that's just shining a lot of light, and it creates a shadow of this bead on the wall. Right, so even though this is a loop, it's sort of aimed straight towards the wall, so you sort of only see the bead going up and down. You don't actually see any circular motion because it's sort of oriented, the bracelet is sort of oriented directly at the wall. But you can see, because it's a shadow, this is exactly the same as the vertical distance, right? From here to here. Like the distance of the shadow on the wall from the center point is exactly going to be the vertical distance. But the vertical distance was here, we said it's theta, so this was going to be the sine of theta, is going to be the vertical position of this bead on the wall when the light shines upon it. So how do we actually create a wave? Well, if you think about it, if we sort of roll this bead around the circle, the actual shadow on the wall will go up and down on the wall, kind of like a wave. Right, so it's sort of like, if you think of sound, it kind of goes, it kind of makes a vibration. So if you make this bead go around the circle, then it actually creates a vibration in the shadow on the wall, which just goes up and down, and we see no circular motion. So, but then we need to sort of be more precise, right? Mathematics is all about being precise. So how do we actually describe it? Well, first thing is we make some simplifying assumptions, is that this is going at a uniform speed. What does that mean? It means it's like in a car, you go at uniform speed, you go at 10 miles per hour, and then you just stay at 10 miles per hour. So in 1 hour you travel 10 miles, in 2 hours you travel 20 miles, in 3 hours you travel 30 miles. So it's about constant speed. So the same notion here is maybe we define an omega called an angular speed. So this is called angular speed. And so an example would be like 10 degrees per second, right? Or 1 radian per second, or something like that. And this means that in 1 second, this bead would have rotated 10 degrees. In 2 seconds, it would have rotated 20 degrees. In 3 seconds, it would have rotated 30 degrees. And then in 0.5 seconds, it would have rotated 5 degrees, right? So it's linearly interpolated, and it just sort of uniformly goes around the circle at this speed. So what have we just described? Well, this means that the actual angle is going to be equal to the angular speed times the time, right? Just as in a car, the distance is the speed times the time. Here now, because it's an angular speed, the angle is going to be equal to the angular speed times the time. Okay, so that's good. And then here we said the position of the bead on the wall was sine of theta. And so we don't want it to be in terms of theta, we want it to be in time. Like, where is this at 2 seconds? Where is this at 3 seconds? Then we just substitute in omega t, and so this graph becomes the sine of omega t. Okay, So that's great. But, and now if we just, graph the whole thing, so I can just erase this. So if we graph it, it'll look exactly like the sine of theta. But now, instead of theta, so remember the wave repeats at 2 pi, right? So here it would be at like theta equals 2 pi. But now theta was equal to omega t. So that means omega t is actually equal to 2 pi. So that means at this point, what is going to be the time? Well, just solving for it algebraically, time is going to be 2 pi divided by the angular speed, or 360 divided by angular speed. So if angular speed was 10 degrees per second, then 360 degrees, or 2 pi divided by 10 degrees, is going to give us 36. So that means this is going to give us 36 seconds for this angular speed, right? It's going to be 360 degrees divided by 10 degrees per second, and that's going to give us 36 seconds to go around this, right? If you recall from our wave definitions, this was called the period. So that means the period of a wave is going to be 2 pi divided by this angular speed. So this is the definition of the period of the wave. So here we have sine of omega t, and this means that if you see a graph that says sine of omega t, you immediately think, okay, it's a wave over time, and this is its angular speed. Okay, so if you see a function that says sine of 2t, this means that the angular speed is 2, and t is going to be the variable. Sometimes it might be x, it might be something else, right? But so this means it's the angular speed. And so then you would know that the period is going to be 2. So here, the angular speed is 2, and then the period is going to be 2 pi divided by 2, which is going to be pi. So that means, in actually pi seconds, or in that amount of time, it's actually going to repeat, right? So in a little bit more than 3 seconds, 3.14 seconds, this wave is going to repeat for sine of theta, or sine of 2t. So this is how to get the period of a wave. But now, okay, and then now let's think about how this thing actually affects it. So this is the angular speed, right? So the faster the angular speed is, the faster this thing is going to be going around in the circle, and then the faster the shadow actually moves on the wall. And then so that means over time, the higher the frequency, right? The higher the pitch of this wave, because the shadow sort of goes up and down much more times in 1 second than before. So this means that the larger this number is, the higher pitch the wave actually is. If it was a sound wave, the higher pitch it would actually be. And then for light, it would just have a higher frequency, so like it would be blue instead of red, or something like that for a wave. So, but now remember the wave. We had the pitch, but we also had the amplitude, right? And there's a problem because with sine, the amplitude can at most be between 1 and -1. I already mentioned why that is, because this is a unit circle. Well, the thing is, we have a bead on a bracelet, and it doesn't really have to be a circle of radius 1. It could be of radius 100, in which case, the circle would be much bigger, and then the shadow would actually go up and go down much more, right? Because, the bead actually went up and went down much more, because it's a much bigger circle. And so how do we actually make a bigger circle? Well, the whole point is this was the radius, right? So if this was a radius, then remember, what is the vertical distance? It's going to be r times the sine of omega t instead. And because this is the maximum, and the maximum we call the amplitude, this means that the radius is actually the same thing now as the amplitude of the wave. So this means that to complete the whole wave graph, we would actually get a times sine of omega t. And yep, so now here, just from sine, we can get the whole graph of any kind of a sinusoidal wave, and we can choose any frequency we want with this parameter, and we can choose any amplitude we want with this parameter. So it's sort of mathematically shows how we can capture wave motion. And so instead of having to draw out a wave and describing it, we can describe it with a simple, concise mathematical formula like this to show that, and you look at it and you go, okay, this is a wave. So let's give an example.